In this video for section 8.5 of chapter 5, we're going to learn another technique for resolving integrals of a special type, and this technique is called the partial fractions technique. So let's take a look at this integral. So we could use the technique of letting x equal sine theta and go through it that way, but that would actually turn out to be a pretty lengthy process because of what we'd be left with when we did those substitutions. There turns out to be a much better way to do integrals of this type. If we notice that the denominator of this integrand can be factored as 1 plus x times 1 minus x, and using that we are able to rewrite that integrand as a sum of fractions, one with the denominator 1 plus x, one with the denominator 1 minus x, if we find out what those numerators a and b need to be to make that equation true. So the way we solve that equation is to multiply both sides through by this denominator, 1 minus x squared. That leaves 1 on the left-hand side. It's a times 1 minus x plus b times 1 plus x. And that turns out to be a easy equation to solve. If we let x equal 1, the left side of the equation is 1. The right-hand side, we've chosen 1 because it cancels out this term on the right-hand side and leaves us just with b times 1 plus 1, or in other words, b equals 1/2. So let's put up here that b equals 1/2. The other value of x that we can choose is going to zero out the other factor on the right-hand side, and that is to let x equal minus 1. If we do that, the left-hand side of the equation is still 1. This factor is zeroed out, and on the right-hand side we get a times minus 1 minus 1, or a times minus 2, or a equals minus 1/2. And so that tells us that, oops, sorry, there's an error here. This should be a times 1 minus minus 1, or a times 2, so a is also 1/2. So dx over 1 minus x squared is 1/2 dx over 1 plus x plus 1/2 dx over 1 minus x. And those are two easy integrals to resolve. They're both ln integrals. The first one is 1/2 ln of 1 plus x. The second one is plus 1/2 times minus ln of absolute 1 minus x. And we can combine these two integrals together to get 1/2 ln of 1 plus x over 1 minus x. Absolute of 1 plus x over absolute of 1 minus x. So pretty certainly easy integrals to do. The complication in doing integrals using this so we see that we get 1/2 ln 1 plus x minus 1/2 ln 1 minus x, which gives us this result. So these integrals using the partial fraction technique are pretty easy to do. The complication is how hard is it to split the integrand into those fractions. Let's take a look at another example, which is example 2 on page 176. This time we have 3 fractions in the denominator, or 3 factors in the denominator, and we're going to want to find how to take this integrand x squared over x plus 1 times x plus 2 times x plus 3 and turn it into the sum of three what we call partial fractions, and those partial fractions would be a over x plus 1 plus b over x plus 2 plus c over x plus 3. When we say what the numerators of these fractions are, a, b, and c in this case, the guideline is that the degree of the numerator, so the degree of the numerator is 1 less than the degree of the denominator. 1 less than the degree of the denominator. And so this, all of these denominators right here have degree equal 1, and all of these numerators here, of course, being constants, are of degree equal 0. So let's follow through with how we find a, b, and c by multiplying through by x plus 1 times x plus 2 plus times x plus 3 to clear out all the fractions. So we get on the left side x squared plus 1, and on the right side we get a, the factor x plus 1 cancels, we get a times x plus 2 times x plus 3 plus b, the x plus 2 factor cancels, so it's b times x plus 1 times x plus 3, and on the c term, the x plus 3 factor, so it's c times x plus 1 times x plus 2. We use that same zero out method. So first we're going to let x equal minus 2. And when we let x equal minus 2, we see that this term and this term are zeroed out, and so what we are left with is minus, on the left hand side, minus 2 squared plus 1 equals 0 plus b times minus 2 plus 1 times minus 2 plus 3 plus 0. This is equal to b times minus 1. This left-hand side is 5. So that gives us b equals minus 5. If we pick x equals minus 1, that then zeroes out this and this term on the right hand side. We get minus 1 squared plus 1 equals a times what? 1 times 2 plus 0 plus 0, or 2a equals 2, or a equals 1. And then let's do x equals minus 3, which gives us minus 3 squared plus 1 equals 0 plus 0 plus 0 plus 0 plus c times minus 2 times minus 1. 2c equals 10, or c equals 5. So we have found all three constants, a, b, and c, and we can set up the three integrals. The three values of a were 1, minus 1, and 5, and so the integrals are dx over x plus 1, minus 5 dx over x plus 2, plus 5 dx over x plus 3. And so that gives us the result very simply from here. Ln of absolute x plus 1 minus 5 ln of absolute x plus 2 and plus 5 ln of absolute x plus 3 plus c. And so there's our result. It's combined together as one logarithm on page 176 in your text. Well, so far we've only dealt with how to separate fractions into their partial fractions in the two cases where the denominator had only what we call linear factors. So we had this set up in case 1, and we had this set up here in our second example. So let's see how we can set this up when we have quadratic denominators, keeping in mind this guideline for numerators and denominators in a partial fraction setup. So let's look at example 3 found on page 176 in your text. Actually, that's example 3 on page 177. So it's dx, and we're going to have two quadratic factors in the denominator, this time x squared plus 9 times x squared plus 4. So the partial fraction setup this time for the integrand 1 over x squared plus 9 times x squared plus 4 is going to actually involve quadratic denominators, right? So this is x squared plus 9, and the other denominator is x squared plus 4. The guideline we said is that the degree of the numerator is 1 less than the degree of the denominator. So let's put a first degree numerator in there, which would be ax plus b, and a first degree numerator here would give us a cx plus d. And then we're going to do the same thing that we did before. We're going to multiply through by this denominator on the left-hand side to clear out all the fractions. So when we do that, what do we get this time? We get 1 equals ax plus b times the x squared plus 9 cancels out, and we're left with x squared plus 4. And we've got the cx plus d, the x squared plus 4 cancels out, and we're left with it being multiplied by x squared plus 9. We want to notice that the zero out method will not work in this case because there is no value of x that will zero out this factor or zero out this factor except values of x that are complex numbers, which we don't want to choose. So we have to use a different method for figuring out the constants a, b, c, and d, and let's find out what that method is on the next blackboard. It's called the method of grouping, and the way we do that first is to multiply out the fractions on the right hand side. So let's copy that over. So we're going to multiply out the right hand side, but when we do that we're going to group the terms of like degree orders together. So we've got what, ax times x squared, ax cubed, b times x squared is bx squared. We've got ax times 9, which is 9ax, and we've got b times 9, which is 9b. Then we've got cx times x squared, which gives us cx cubed, then d times x squared, which gives us dx squared. Cx times 4 is 4cx, and d times 4 is 4d. And so that tells us that on the right hand side we have a plus c times x cubed plus b plus d times x squared plus 9a plus 4c times x and plus 9b plus 4d. And this has to equal the 1 on the left-hand side, but we're going to rewrite that 1 in this way as 0x cubed plus 0x squared plus 0x plus 1. So we then get 4 equations, right? We have a plus c equals 0, we have b plus d equals 0. We're matching, right, the coefficient of x squared on this side with the coefficient of x squared on this side. We have the x coefficients equal, so 9a plus 4c equals the coefficient of x on the left side, 0. And then finally we have 9b plus 4d equals 1. So let's write those four equations on the next blackboard. So if we start with this first equation, it gives us that a equals minus c. And the second equation gives us that that b equals minus d. If we plug a equals minus c into 9a plus 4c equals 0, we get what? 9 times minus c plus 4c equals 0, 5c equals 0, minus 5c equals 0, or c equals 0. And if we plug b equals d into this equation, b equals minus d into this equation, we get 9 times minus d plus 4d equals 1, minus 5d equals 1, d equals minus 1/5, and because d equals minus 1/5, we also have, because b equals minus d, that b equals 1/5. And so we can set up the integral on the right. The integral is on the right hand side. So the two integrals that we get are this with b equals minus 1/5, and this with d equals 1/5. Remember from a previous derivation that dx over a squared plus x squared is 1 over a tangent inverse of x over a plus c. That we saw this derivation. I'm not sure we saw exactly this derivation, but we saw a problem like it in the previous section where a was a specific constant, and so we can apply that in both of these cases, and we get what, 1/5 tangent of 1/5, 1 over a is 1 over 2, and it's tangent inverse of x over a, and a is 2, and then minus 1/5, the a is 3, tan inverse of x over 3 plus c. And so that completes this problem. This problem was made a fair amount easier, though, because we did not have both a and b being non-zero. We only had b being non-zero, and the a was zeroed out, and the c was zeroed out, and we had a d. What happens when we get the ax and the b and the cx and the d? Well, we're going to see that on this next example. So it might be a good time to take a little break. This next example is going to take us 6 or 8 minutes to go through. So take a little break, come back, and let's do this example. The partial fraction setup for this is going to look a little bit different than the ones we've done before. We've got these three denominators here. This one, the x plus 1 quantity squared, and the x squared plus 2 to the fourth. But this denominator here is repeated, and when we have a raised to a power higher than 1, which we call repeated, when we have that kind of a denominator, here's how we set it up. A over x, that makes sense. B, actually let's do it in 2 steps. Let's say that the x plus 1 quantity squared is a quadratic denominator. Let's go to another blackboard and show how we set it up when we have a repeated denominator. So let's say we have x squared in the top, and normally what we would do is we would say, okay, that's a quadratic, I'm sorry, we have x squared in the bottom. That's a quadratic denominator. We should have a numerator that is 1 degree less, and we could set up that way, but watch what happens when we simplify this or rewrite this as two fractions. That's ax over x squared plus b over x squared, which simplifies to a over x plus b over x squared. Well, this turns out to be a much preferred way to write the partial fractions, because then they're much easier integrals to do than this integral would be. And so the guideline for when we have repeated factors is to start at power 1 and use the linear numerator, which would be just a constant a, and then increase the power and again use a linear numerator, and then you've got it resolved. So if we generalize a little bit further, let's suppose we had x cubed, and then we would have what, a x squared plus b x plus c, but we would write that in its simplified form as a over x power 1, another constant numerator power 2, another constant numerator power 3. So we start at power 1, then go to power 2, then go to power 3, until we get all of the repetitions in. So back to where we were, we would write this as ax, or a over x, plus b over x plus 1, plus what would be next? C over the x plus 1 raised to the next higher power, which is x plus 1 squared, and then we need a dx plus e over the quadratic factor x squared plus 4. So we're going to go through and multiply by this denominator on the left side to clear out all the denominators, and let's see what we get then. So we get x squared on the left. The a is times x plus 1 squared times x squared plus 4 because the x cancels. The b is times x, and then x plus 1 to the first, because one of the x plus 1's cancels, times x squared plus 1. The c is times x, the x plus 1 quantity squared cancels, so it's c times x squared plus 4. And then the dx plus e, the x squared plus 4 cancels, and so it's multiplied by x, and x plus 1 quantity squared. Well, in the textbook, you see that we have all of these terms multiplied out. To make the computations easier, and so if you look at the top of page 179, let's see what we have. So this a turns out to be multiplied by x to the 4th plus 2x cubed plus 5x squared plus 8x plus 4, and then the b term turns out to be multiplied by x to the 4th plus x cubed plus 4x squared plus 4x, and then I'm going to fill in the c and the d and the e below this. So let's notice that the x to the 4th is multiplied by a, b, d, and e. The x to the 3rd is multiplied by 2a, 1b, 1c, and 2d. The x squared is multiplied by 5a, 4b, c is missing, 1d, and 2e. The x to the 1st multiplied by 8a, 4b, 4c, the d is missing, and 1e, and the constant term, x to the 0, is only multiplied by a 4. So let's set that up in what we call a matrix that looks like this. Okay, so back here we saw that x to the 4th was multiplied by 1a, 1b, c wasn't there, d and e. So a, b, d, and e. Sorry, there's a mistake here. This e term should have x to the 4th missing, and it should have an x cubed here. Okay, so when we go through and identify the coefficients of x to the 4th, we got 1a, 1b, 0c, 1d, and 0e. So let's fill that in on our matrix. We said 1a, 1b, 0c, 1d, and 0e. Now when we look at this x cubed column, we see that it's 2a, 1b, 1c, 2d, and 0e. So let's fill that in. So here are the x cubed coefficients filled in. The x squared coefficients are 5, 4, 0, 1, 2. Let's fill those in. And now let's look at the x coefficients, which are 8, 4, 4, 0, 1. Let's fill those in. So we filled in the x coefficients here. And now let's finally look at the constant coefficients, which are 4, and then all the rest are 0. So let's fill those in. So those are filled in. And now let's go back and note that all of this is equal to x squared. And so in this column of the matrix here, which is the polynomial column, x to the 4th on the left side 0, x cubed is 0, x squared has a 1, x has a 0, and x to the 0 has a 0. So the only coefficient in the p column that is non-zero is the x squared coefficient right here. So this is called a matrix. If you plug this matrix into your calculator, it will solve it for you. When it solves it for you, it looks like this. So we have the 5 columns, and in the first 5 columns representing A, B, C, D, and E. And in this last column we actually have the solutions, because this first row says 1a equals 0, so that says the solution for a is 0. This second column says that 1 times b, with all the other constants being 0, equals 3/25. So here's the solution for b, and then correspondingly here's the solution for c, for d, and for e. And so we can set up our integrals now and work to resolve them. So here are the 4 integrals, and they're all relatively easy to do. The first one is 3/25 ln absolute x plus 1. The next one is like integrating x to the minus 2 dx, which is minus 1 over x, right? So this is minus a fifth, so 1/5 times x plus 1 in the denominator. The next one is a u substitution problem with u equaling this denominator, and then the numerator is 1/2 du. So that gives us minus 3/25 times that 1/2, and then times ln of that denominator, x squared plus 4, because it becomes a du over u integral, right, after substitution technique. And then the last one is a tan inverse with a being 1/2, so it's 8/25 times 1/2 tan inverse of x over a, with a being 2. And so there's our final answer for this integral. It's a protracted process of resolving what the constants but once we get the constants a, b, c, and d, the integrals are not difficult. So all of the work is involved in multiplying out this this right-hand side here and grouping the terms of like powers together, right, in columns, so that we know what the coefficients of x to the 4th, x cubed, x squared, etc. are in terms of a, b, and c. We line all that up into a matrix. We pop that into our calculator or some other program. We find the solutions. A, B, C, D, and E are displayed here in this last column. And then we set up the integrals, which are, as we said, easy to do. So that concludes this video on the partial fractions technique, with probably some more examples to come in a later video, and certainly a lot of practice to come in the classroom to refine this technique.